Hi there, welcome to APES Chapter 17, Lecture Video Part 2. Let us begin. This section will begin where we're going to talk about, global wind patterns and things of that nature and how those all form and what they're, why and how these air patterns move, okay? So this section is going to have a lot of pictures, a lot of visuals to describe the content. Let's begin. A cell, all right? So around the Earth, we have different masses of air, large masses of air, and they're called cells. We have around the Earth three major kinds, and their names are Hadley cells, and they are here and here, just from where the equator is to about 30 degrees north, equator to 30 degrees south. We have what's called Ferrel cells, which are between 30 north and 60 north, or between 30 south to 60 south. And we have another large mass air circulation called a polar cell from 60 north to the very top 90. So the top North Pole and South Pole are 90 north and 90 south. So we have divisions of the Earth and these wind patterns or these air mass circulation patterns that take place. It's very important that you understand these because they tell you a lot about global climate and what you would expect to happen in a particular place. And they kind of let you know what happens in San Diego. Why do I talk about San Diego? We're right here. We're about 30, just above 30 degrees north, around 31 degrees north right here, north latitude. And we're in one of these zones that falls between two of these air mass cells. We are between the Hadleys and the Ferrels, and because of that, this is why San Diego has such beautiful weather. And I'm going to talk about it shortly. All right, so let's begin. All right, so here's what you got. Hadley cells. These are the ones from the equator to 30 north and equator to 30 south. Well, what happens at the equator? Because all that solar heating takes place at the equator, you have a lot of air rising at the equator. Rising air, low air pressure. So what do you expect at the equator? Rain, and lots of it. That's because of this rising air, this low air pressure, all that sun is smashing into that area, and you get a lot of rain at the equator. Tropical areas, lots of rain. But what does a Hadley cell do? Well, remember we learned in our last lecture about what's called convective currents. So warm air, it rises, it loses its heat, it loses its precipitation, and then in this case it goes north or south, but let's just talk about northern hemisphere. The air travels north and it gets drier and drier and drier and drier and gets colder and colder. And then when that air gets to about 30 degrees north, it starts to sink. So this picture is showing you a convection circulation. It rises at the equator, travels north or south, in this case, north or south, and then it sinks right around 30 degrees north. That sinking air, high pressure. At 30 degrees north, what do you get? High pressure usually, which means you're going to have less rain, clear skies, sunny skies. We're at 31 degrees north over here in San Diego. So we have this generally a high pressure system where we live. Why do we generally have a high pressure system? Because the air descends right around 30 degrees north. This is one of the reasons why San Diego has just such beautiful sunny climate all year round. Also, being 30 degrees north means we're not that cold. We're not quite too cold yet. Our ocean off our coastline stays relatively mild. So we are on a coastline, which helps control our climate and keeps it moderate because our ocean never gets colder than around 55 or 50, and it never gets warmer than 75 to 80. So we have a moderate climate, sunny most of the year because we are right around 30 degrees north latitude. So air descends on us, creating high pressure where we live. So they do it also in the south. It rises at the equator, it sinks at 30 degrees south. Anywhere along 30 degrees south, you'll probably find the same type of high pressure expectation. Deserts are usually found around 30 degrees north. Okay. You're going to find a lot of deserts, and you're going to find Mediterranean climates, kind of like San Diego's climate, right around 30 degrees north and 30 degrees south. To have our climate, you need to be, we are desert like, but we are not quite a desert because we have a coastline that helps moderate temperatures for us significantly. So to have San Diego's climate, you go down to Australia, which is around 30 parts of Australia, right around 30 degrees south, and they're coastal and they have similar climate, similar weather as San Diego. And that's what you expect. All right. So it rises at 0 or the equator, it sinks at 30, low pressure rain, high pressure sunny, clear skies right around 30. All right. So we just talked about the Hadley cells. Now let's talk about the Ferrel cells. Well, the Ferrel cells also sink at 30 degrees north, okay? But they rise at 60 degrees north. So since 60 degrees north is where they rise, 60 degrees north is where they're going to have low pressure and they're going to have a lot of rainfall. At 30 degrees north, we already talked about it, high pressure because it's sinking, high pressure, clear skies, no rainfall. 60 degrees north or 60 degrees south, air is now rising and you're going to have low pressure and you're going to have clouds and rain. Seattle is an area that is known for a lot of rainfall, and that's because of how far north they are. They're far north. Places in northern Europe have a lot of rain. They're known for their rain because of their location. So anywhere located near 60 degrees north is going to have a lot of rain. Okay, that's what you're going to expect there. A lot of precipitation. Polar cells, now, same thing. They're right at the border of the Ferrel. It's rising at 60 degrees north. Once again, low pressure, rainfall there, but it sinks right at the top of the earth and right at the bottom of the earth. Okay, that's where the high pressure is. You have sinking air. You have high pressure at the North Pole and the South Pole. So you have very dry conditions, very little precipitation at the North and South Poles as a result of the polar cells. All right. Well, because the Earth spins, it spins like a top. Because the Earth spins, these winds are not attached to the Earth. The water is not attached to the Earth. Wind is not attached to the Earth. So because the Earth spins, things that are not attached to it are going to take a curving pattern when they move along in the air or even in the water. That is called the Coriolis effect. So it has to do with the spinning of the Earth and how things are deflected. Objects that are not connected to the Earth will be deflected as they are moving as a result of the Earth's spin. In the northern hemisphere, okay, they are deflected towards the right. And in the summer, imagine if you're moving this way, you're being deflected to the left. So in the southern hemisphere, things will be deflected to the left. In the northern hemisphere, things are deflected to the right, okay, or clockwise versus counterclockwise. Those terms are sometimes used. Winds on the Earth. Well, right at the equator, the doldrums, very little winds there, okay? Very little winds right exactly at the equator. All right. Trade winds. These are just north and south of the equator, and these ones move from the east towards the west. Okay. They move from the east towards the west, east towards the west. So you have the northeast and the southeast trade winds here. Westerlies. They move from the west to the east, and they are between 30 and 60 north. Now, winds are named after the direction from where they come from. So a western wind is moving to the east. An eastern wind, like the trade winds, are an eastern wind. Why? They come from the east and they go to the west. All right. In this case, these trade winds are a southeast trade wind. Why? They come from the south. Okay. They come from the southeast and they go from that direction. That's how they're named. Winds are named from the direction from where they come from, not where they are going. So westerlies winds come from the west, go to the east. Okay. And easterlies are up here between 60 north and 90, or 60 south and 90 south. And these are doing the opposite of westerlies, and they are going from the east to the west. Hurricanes. Well, when you have tropical waters where you have a lot of evaporation, you have low pressure systems, and they have a lot of heat and a lot of energy. The Coriolis effect, I just said, things that are not attached start to spin. So you have these giant storms that start to form. Okay. These storms that start to form start traveling, and then when they hit land, they start releasing their moisture. As they hit land, they start to weaken because they've lost a lot of their energy, and when they lost it as precipitation on the land or even the coastline area. So these are huge storms, tropical storms, carrying a lot of moisture. They bring a lot of wind. They bring a lot of rain, heavy, heavy rainfall. By the way, sometimes they're called cyclones, depending on which ocean you are in, okay? So it depends on whether they're called a hurricane. Hurricanes are normally in the Atlantic. I've heard typhoon, that term has been used before, typhoons and cyclones. They're all similar terms. They're these giant storms. They're tropical storms. It depends on which ocean, whether they call it like I said, a typhoon or a hurricane or another term like a cyclone. Tornadoes. Well, when warm air and cold air meet, they run into each other and some air rises and some air sinks. And once again, Coriolis effect. Things spin. Things are not attached to the earth. Earth is spinning. Things that winds, when they run into each other, they start moving and they start rotating. And that is why you have tornadoes. Air pollutants, real simple term, things that are released to the atmosphere. They could be gas, they could be solids in the form of what's called particulate matter. All right. So they affect these things that are released there. Some of them affect climate, some of them affect the air, some of them make it hard for us to breathe. All right. Outdoor air pollution, there's indoor and outdoor air pollution. Outdoor air pollution diffuses in many directions, is probably not quite as bad for us, but it could be long term. Why do I say it's not quite as bad for it? Like I said, because air is in constant motion, it could diffuse. But if you have it inside your house and you're always in your house, you're going to be exposed to it in a great deal. Some pollution we get on Earth is natural. Like, for example, when you have a forest fire, lightning bolt starts a forest fire somewhere, and next thing you know, you have a large catastrophe sometimes, potentially. Fires are natural, but the ashes they create become particulates, and what is released when they burn become air pollutants. So some pollution does come from natural sources. When volcanoes erupt, pollutants enter the air that are natural. They were not man-made or anthropogenic. And here's volcanic eruptions. A lot of stuff is released from a volcanic eruption. A lot. Particulates and chemicals. It is believed that because of the heavy clouds that are released during volcanic eruptions, some of the matter that is released and even some of the gas particles reflect light back to space. So when they reflect the light away from the Earth, aerosols generally cool the atmosphere. How do they cool it? Well, they reflect light and radiation away from Earth, and then the Earth will then feel cooler as a result. So the term aerosols, they reflect light back into space, make things cooler. They are commonly released during volcanic eruptions. When there's volcanic eruptions, they can change air travel. Sometimes there's no visual, you can't even see depending on how bad an eruption is. So major problem for pollution when you have volcanic eruptions. Dust storms. Well, dust blows all the way from Africa to South America and all of the Americas, basically, for that matter. What is blowing them across the ocean? Well, they're blown across by winds, by the trade winds in this case, that go from the east towards the west. So these are just north and south of the equator in those areas. You're going to have winds that are blowing towards the west, okay, towards the west from the east, and these trade winds move the wind in that direction. Okay, and that comes from Africa and ends up going this direction, west towards the Americas, basically. And then the Americas get all this dust that came from Africa. So it is pollution that ends up there. When does it also happen? Dust storms also happen the Great Plains. If you overgraze, you overfarm, the Dust Bowl happened here in the United States. When you overgraze and have a lot of exposed soil to erosion, excessive grazing, desertification, things of that sort, becoming more desert-like, and you now have the potential of dust storms. Pollutants are classified as, and air pollutants are classified as two ways, either a primary or a secondary. Well, primary pollutants is what's released from a source. Primary, something that could be made and released from a source as a primary pollutant, okay, could also sometimes be a secondary pollutant. It's kind of confusing. Secondary pollutants happen when primary pollutants react, all right, and they form something different. All right, so let me give you an example so you understand primary versus secondary. So we burn fossil fuels in a coal burning electric generating facility, all right, power plant. And when you burn coal, sulfur dioxide is released. So sulfur dioxide is released directly from the source. It is a pollutant, a primary pollutant. That sulfur dioxide then reacts in the air with water and can form sulfuric acid and then fall to the earth as acid precipitation. That acid was formed as a result of a reaction with sulfur dioxide and water in the air, forming that secondary pollutant. So secondary pollutants form as a result of primary pollutants reacting. So when something was released, it's primary. So for example, soot from a volcano, released from a volcano, primary. All right. Your car releases carbon monoxide, primary, or your car releases carbon dioxide, primary. Those things then can react, okay, and form other pollutants. For example, a common one is smog, and tropospheric ozone is I mentioned earlier. Ozone is good. Ozone is good when it's in the stratosphere blocking ultraviolet radiation. Ozone in the troposphere, that means ozone on the ground, is not good. How does it form? Well, a bunch of these volatile organic compounds and things on Earth are released from our cars and all these things that we're burning. Those things react together and ozone forms at the ground level area. It's called ground level or tropospheric ozone. This stuff is pretty bad for us. And then this ozone further reacts and leads to smog in the air. All right, brown smog in the air. So things that react and form something else, what is formed, that thing that is formed is secondary. If it's directly released, it's a primary pollutant. Stop there.